Hi, in this lecture we will build our pixel aware module. Previously we created new keyframes using our generate new frames with the cross frame attention and shape aware module. And all these frames are available in this folder, output keyframes folder. We will use them with our pixel aware module. Firstly, this function used SD with the cross-frame attention and shape-aware module and pixel-aware module will take all these arguments. The first one is x0 bar IINU, which is this one here. And we have also our scheduler, the mask between the first and the current keyframes after resizing and make the shape of it equal to the shape of any latent. Okay, and we have also the mask between the current or the previous keyframe and the current keyframe. And here the shape of this mask, it is also similar to the shape of any latent. The next argument is this one here, the forward optical flow between the first and the current keyframes, and the forward optical flow from the previous to the current keyframe, the latent of the current keyframe, the Kenny input that related with the current keyframe, the Kenny input that related with the first keyframe, the text condition, and the current keyframe number. And we have also this normalized wrapped grid FWD latent. This tensor will have the new locations. We will use this one with our grid sample method to wrap our input latent. Our input latent here, it is the latent of the first keyframe. We will wrap it to the latent of the current keyframe using this tensor. And here we will pass the width and height of the generated image or generated keyframe, the guidance scale. Here we will make it 7.5. By increasing this parameter, we will increase the importance of our text condition in the generation process. And here we will make conditioning scale equal to 0.7. This argument, it is related with our control net. And here this argument will specify the first time step that we will start with in reverse diffusion. And here we have this argument. This one will specify how many times we will use or we will apply our shape aware module. And here we have this parameter, TP parameter, will specify the number of time steps that we will use our pixel aware module with. And here we have this parameter, threshold parameter, will specify the threshold that we will use here. Previously we used 0.02, but now we can change it. Here in this get flow and mask, we have another argument which is threshold, which is by default equal to 0.01. You can increase it or decrease it as you want to get the best results. And here we created this global argument gate attribute. Okay, it is something important for our cross frame attention process. And here what we will do, we will make this M capital equal to M1 and I, which is the mask between the first and the current keyframe. And the shape of this mask, it is equal to the shape of any latent. Now we will make this FWD equal to normalized wrapped grid FWD, we will use this one to wrap our input latent to the current latent. And here what we will do, we will create this loop here, and here firstly we will make attribute gates equal to I1, okay, and here we will create our latent input 1 like this, and here we will scale our latent model input 1, and here we will create our control net condition 1, and here we will pass it through our control net, and we will pass also our text prompt and our conditioning scale, and we will get these two things. And here we will use our U-network to get the predicted noise that related with the first keyframe. Here we will do classifier free guidance, and here we will make attribute gate equal to I, and here we will create latent model input I, and here we will scale it. Here we will create control net condition I, and here we will use our control net. We will pass our latent model input I, our text condition, our control net condition I, and our conditioning scale to get these two things here. We will pass them through our U-network, and we will pass also our latent model input to get our predicted noise that related with the current keyframe. Here we will do also classifier free guidance, and here what we will do, here we will check if we finished the first time step. Actually here we will make TD equal to 1, and we will also check if we are working on the second keyframe or more, because as you know our shape over module needs our first keyframe, keyframe 1, and the current keyframe. So our shape over module needs 2 keyframes to work. Here we will define this variable, k variable. This one will have the index of the next time step in reverse diffusion. Here we will use this function to time step 0 function to, and we will pass our latent 1, which is the latent that related with the first keyframe, our scheduler, our current time step, and the predicted noise, the predicted epsilon that related with the first keyframe. So we will get this latent 1 at time step 0, and we will also get latent I at time step 0. Here we will use our to time step 0 also. We will pass our latent I, our scheduler, current time step, noise prediction I, and here what we will do, we will use our grid sample to wrap our latent 1 at time step 0 based on this tensor FWD, and we will get wrapped latent 1 at time step 0. Now we will combine all these latents together. So now wrapped latent 1 at time step 0, it is equal to, here we will take just the unincluded regions from this wrapped latent 1 at time step 0, and we will multiply our latent I at time step 0 by this mask here. So by doing this we will take just the occluded regions from this latent I at time step 0, and here we will combine them together to get this latent I at time step 0. And here we will check if we reached the final time step in reverse diffusion. At this case we will make alpha bar t minus 1 equal to 1. Otherwise we will make alpha bar t minus 1 equal to scheduler dot alpha as cumulative product, and here we will put the index or we will put the next time step in reverse diffusion. And here what we will do, we will create this variable xt minus 1 I, which is equal to latent I at time step 0 times the square root of alpha bar t minus 1 plus the square root of 1 minus alpha bar t minus 1 times the predicted epsilon that are related with the current keyframe. So here actually we did DDIM, and here we will make the current latent equal to xt minus 1 II and latent 1 equal to xt minus 1 I1. And here, if we finished the first time step, so now we don't need to use our shape aware module anymore, and we will use our pixel aware module only. Here we will create this variable, k variable, which will specify the index of the next key time step in reverse diffusion. Here we will create a noise. We will take Gaussian noise. The shape of this noise should be equal to the shape of any latent. Here we will add this noise to our x0 bar II new to get xt minus 1 bar II new. Here we moved our x0 bar II new to time step t minus 1 or t minus delta t. Here we passed the next time step in reverse diffusion, and here we will find the intersection regions between these two masks, M1 and I and Mi minus 1 and I. We will fill these intersection regions with our original current latent that we can take from our U network. And here what we will do, xt minus 1 II equal to this new mask times xt minus 1 II plus 1 minus this mask here times xt minus 1 bar II new. So actually we are working on this place here, and we will make our current latent equal to xt minus 1 II, which is this one here, and we will make latent 1 equal to xt minus 1 I1. And if we finished the time steps that we won't use our pixel aware module with, in this case we will just do our normal reverse diffusion process. We will just make our latent I equal to xt minus 1 II and latent 1 equal to xt minus 1 I1, and we will take these things just from our U network without using our shape aware or pixel aware modules. Okay, and that's it. Now let's talk about this function here. Here we created this function generating new frames with the cross-frame attention and shape-aware module and pixel-aware module. And here this function will take these arguments. The first argument is generated keyframes directory. Here we will put our new keyframes in this directory, and this one latent directory. We talked about this one previously, and this one, and this one. And here we put this argument, the threshold argument, which is by default equal to 0.01. Here we will put the names of our latents in this list here. Let's call it latents names list, and here we will sort this list. And here we will create this list, Kenny inputs names list, and we will sort this list. We will take Kenny input 1 image, and we will take latent input 1, which is the latent that are related with the first keyframe, and we will take it from this directory like what we did previously. Here what we will do, we will take our original first keyframe. We will convert the order of the color channels from BGR to RGB. It is something important actually. And we didn't do that previously in shape-aware module lectures, so please do it. Okay. Now we will create this loop here. We will pass it through each latent, and we will get the current original keyframe. We will convert the order of the color channels for this keyframe, and here we will check if we are working on the first keyframe or on the second keyframe. At this case, we will do the following. We will make keyframe 1 equal to keyframe I minus 1. Okay? And now what we will do, we will take this generated keyframe, the current generated keyframe, because it is something important for our pixel-aware module. We will convert the order of the color channels from BGR to RGB. So now we have this generated keyframe I, this one created with just using our shape-aware module and cross-frame attention, and without using our pixel-aware module. We just used this function to get these generated keyframes with just using shape-aware and cross-frame attention. And now what we will do, we will create this variable II new, this tensor. Here we should convert this one from NumPy array to PyTorch tensor, and we should add the batch dimension with length 1, and we should change the order of the dimensions. We will put the channel dimension in this place here, and we will put the width and height dimension here and here. And here we will keep our batch dimension at the same place. The length of this dimension equal to 1 actually. Here we will check if we are working on the first keyframe. At this case, we will make generated keyframe I equal to generated keyframe 1, and we will make generated keyframe I minus 1 equal to generated keyframe I. And here we will make all the keyframes equal to the generated keyframe I, because here we are working on the first keyframe. So now we have just one keyframe here, one generated keyframe. So we will make generated keyframe 1 equal to generated keyframe I, and generated keyframe I minus 1 equal to generated keyframe I. And here we will make I1 in U equal to II in U, which means that the first generated keyframe with just using cross-frame attention and shape-aware module should be equal to the current generated keyframe with just using cross-frame attention and shape-aware module, because here we have just one generated keyframe. We are working on the first generated keyframe. And the same thing here, II minus 1 equal to I1 in U, which is equal to II in U. Or we can put this here also to be more clear. And here what we will do, if we are working on the second keyframe, at this case we will make generated keyframe I minus 1 equal to generated keyframe 1. Okay, and we will convert it into a tensor. II minus 1 equal to, here we will convert this one into tensor, and we will add the batch dimension, and we will change the order of the dimensions. Here is the first dimension, which is the batch dimension, and the second dimension, which is the channel dimension, and the third dimension, which is the height dimension, and the last dimension, which is the width dimension. And here what we will do, if we are working on the, for example, the third, fourth, fifth keyframe, we want to generate the third keyframe. At this case, what we will do, now we will take our generated keyframe I minus 1 from our generated keyframes directory, okay, which is this one here, okay, So now we have our generated keyframe I-1, and we will change the order of the color dimension. So now we have this generated keyframe I-1. We will also read the original previous keyframe. So keyframe I-1 equal to, and we will take this one from our frames directory, which is this one here. This one will have our original frames of our video. And here what we will do, we will change the order of the color dimension, and here we will convert it into a tensor, and we will add our batch dimension, and now we have this II-1. Here we pass this one to it to get this II-1, and we have our original previous keyframe, and we have also our keyframe I, and we have also our keyframe 1. That's really good. Now what we will do, we will use our optical flow model. We will pass our keyframe 1 and keyframe I, and we will pass our threshold to this get flow and mask function to get the mask between the first and the current keyframe, and the forward optical flow between the first and the current keyframe. That's good. Now we will find the mask between the previous keyframe and the current keyframe, the occluded mask, and the forward optical flow between the previous and the current keyframe. We will use our get flow and mask. We will pass our keyframe I-1 and keyframe I and our threshold. And here what we will do, we will take the height and width of our II new, which is the height and width of any keyframe. We will create a Y list and X list based on these two things here. We will change the width and height of this FWD 1 to I based on these two things here, the height and width of our II new. Here what we will do now, we will create a list of Y locations and X locations, and here we will resize our FWD 1 to I based on these two things, the height and width of our I1 in U, and here we will get this FWD 1 to I. Here what we will do, we will do the same thing for our FWD I-1 to I. We will also resize it, and here we will stack these two tensors together and adding this FWD 1 to I to get this wrapped grid using FWD to I. And we will stack these two X and Y locations together, and we will add our FWD I-1 to I to this tensor, and we will get this wrapped grid using FWD I-1 to I. Here we will do normalization. Here we will take the shape of FWD I-1 to I, and what we will do, we will type normalized wrapped grid wrapped X grid FWD 1 to I equal to, here we will multiply 2 by wrapped grid using FWD 1 to I. Here we will take the X locations, we will divide the resulted tensor by the width minus 1, and we will subtract 1 from the resulted tensor. We will do the same thing for our wrapped Y grid, and here normalized wrapped Y grid FWD 1 to I equal to 2 times wrapped grid using FWD 1 to I, and here we will put the index of our Y locations. Here we will divide this resulted tensor by the height minus 1, and here we will subtract 1 from the result. Okay, now what we will do here, we will type normalized wrapped x grid fwd I minus 1 to I equal to, we will do the same thing here, 2 times wrapped grid using fwd I minus 1 to I, and here we will put the index of this of x locations divided by w minus 1 minus 1, and here we will type normalized wrapped y grid fwd I minus 1 to I equal to 2 times wrapped grid using fwd I minus 1 to I, and here we will put the index of the y locations divided by the height minus 1 minus 1. Here we will stack normalized wrapped x grid fwd 1 to I with normalized wrapped y grid fwd to I. And we will do the same thing here. Normalized wrapped grid fwd I minus 1 to I equal to, here we will stack this normalized wrapped x grid fwd I minus 1 to I with normalized wrapped y grid fwd I minus 1 to I. Yes. Now we will do wrapping. Wrapped IINU equal to, here we will use grid sample method. What we will do actually, we will convert this I1NU into tensor, and we will specify the type of this tensor. And what we will do here, we will pass our normalized wrapped grid fwd 1 to I, and here we will specify the type. Okay, so now we will get our wrapped I1NU, and here we will get wrapped I minus 1 NU. Here we will pass our I minus 1. You can call it I minus 1 NU, okay, like this one here, no problem. So now we will pass it, we will change the type of this tensor, and we will send it to our device. Here we will pass our normalized wrapped grid fwd I minus 1 to I. Okay, so now we will get wrapped I minus 1 NU. Here we will get the shape of any latent, we will get the height and width of any latent. Here what we will do, we have this capital, the occluded mask between the first and the current keyframe. We want to resize it to make it the shape of it equal to the shape of any latent. So let's call it m small 1 and I. And here what we will do, we will change it to numpy array. We will do the same thing to mi minus 1 and I. We will get m small I minus 1 and I. We will convert this one into numpy array. Okay, so now we will do resizing. Here we will type m1 and I. Here we will put 0, and here we will put the new size. So now we have this m1 and I. We will do the same thing for our mi minus 1 and I, and we will get this one mi minus 1 and I. Here we will change the type of this tensor to, or this numpy array to PyTorch tensor. We will convert it into PyTorch tensor. Now we have this PyTorch tensor. We will do the same thing for our mi minus 1 and I. And here we will add another dimension, which is the batch dimension, to our m1 and I, and we will do the same thing for our mi minus 1 and I. And we will put another dimension, okay, to our m1 and I, because as you know, any latent will have 4 dimensions: the batch dimension, the feature maps dimension, the height, and the width. Okay, so now we will add feature maps dimension, and we will repeat it 4 times, because in any latent, this dimension, the length of this dimension equal to 4. So we will do the same thing for our mask. So m1 and I equal to m1 and I dot repeat, and here we will repeat this one 4 times. Okay, and the same thing for our mi minus 1, we will repeat it 4 times, and we will do something similar to our m capital I1 and I. And the size of this one, actually the width and height of this one equal to the width and height of any keyframe, but this one will not have the color dimensions, and we will put this dimension in this location in the same place of our feature maps dimension, and we will repeat it 3 times because this dimension, the color dimension, will have 3 channels. Okay, so now we made this mask something suitable to multiply with any keyframe that we have. We will do the same thing to our mi minus 1 and I. And now what we will do, here we will compute I bar new. Okay, this one here, we will learn how to compute this one. So I bar new equal to m1 and I times, here we will multiply our capital M I minus 1 and I times I new plus 1 minus M I minus 1 and I times wrapped I minus 1 in u. Okay, we have this one here. We will multiply this one by M1 and I plus 1 minus M1 and I times wrapped I1 in u. We will divide this I bar new by 255, and here we will put with torch.no gradient, and here we will use e star function. We will pass our I bar new to this function. But what is inside this function? Why we don't just use our encoder? Okay, here is our e star function. This function will take just one argument, which is I bar. Here we will make the values of this I bar between -1 and 1, because it is something important for our encoder, part of our variational autoencoder. And here we will use our E, our encoder. We will pass this new keyframe to our encoder, and we will get x0r. And here we will make x0r equal to decoder input. We will pass this one through our decoder, and we will get I capital R. We will make this I capital R equal to encoder input. We will pass this encoder input through our encoder to get this x0rr. We will subtract this x0rr from this x0r to get the error tensor. Actually, this encoder will create an error, so we need to reduce that error. It's not a good idea to use it directly. So we will reduce this error. We will add this error to our x0r to get this x0r with a small error. And finally, we will multiply this x0r with a small amount of error by variational autoencoder scaling factor. By using this E star, you will reduce the error of our encoder. And now we have our x0r, which is our x0 bar I new. So now we have this one here. Okay, now what we will do, we will create this variable current keyframe latent path and current keyframe Kenny input path and Kenny input I and latent input I, and here we will take the height and width from any latent input 1. We will create our X and Y locations, and we will resize our FWD1 to I to get this FWD. We will add this FWD to our tensor here to get wrapped grid using FWD latent. Here we will take the shape of this grid, and what we will do, we will normalize our X locations and Y locations by doing the same way, and here we will stack them together to get this normalized wrapped grid FWD latent. And here what we will do, we will use our function. Okay, our use SD with the cross frame attention and shape aware module and pixel aware module. We will pass our x0 bar II new and scheduler and m small 1 and I and mi minus 1 and I and fwd 1 to I and fwd I minus 1 to I and latent input I, Kenny input I, latent input 1, Kenny input 1, CP, current latent name, normalized gradient FWD, width and height, guidance scale, conditioning scale, first time step, TD equal to 1, TP equal to 6, threshold equal to 0.01. Here we will apply our pixel aware module and the first 6 time steps in reverse diffusion. Okay, that's it. And now we will call our function generating new frames with the cross frame attention and shape aware module and pixel aware module. And here we actually changed our prompt to this one here, digital painting man CG style. Okay, now let's see the results. Here's our first generated keyframe, the second one. That's really good. As you can see, the background is the same textures and shapes. And now we can say that this person here is similar to this person here. And let's move to the third keyframe. That's good also. And this one is good also. This one. Okay, that's really good actually. In the next lecture, we will learn how to convert these keyframes to a video using EB Synth. Thanks for watching.